introduction and the kind invitation to speak here today. It's a great pleasure for me to speak at the McDonald Institute seminar series. And as Aaron mentioned, I will talk about the origin of neutrino masses and what kind of role gravity could play in this game. And this is ongoing in previous work in collaboration with Kia Dwali, Georg Raffelt, and other people. So you all know that there is a, how can I get rid of this upper panel? Sorry, I try to get rid of this upper panel here, but maybe this doesn't work.
Oh, is that your Zoom panel? We don't see it.
Yeah, I see my Zoom panel up there, but it's okay, it doesn't matter.
Yeah, we
I can see the slides, so that's fine. All right, okay. So you all know that there's a huge gap in between the masses of the neutrinos and the masses of the other fermions in the standard model. And this is widely seen as unnatural, so many people believe that the neutrino masses are not generated through the conventional Higgs mechanism. And this is one of the main motivations for building new models beyond the standard model of particle physics. So the usual route that people take is they go to very high energies, for example, with a famous seesaw mechanism, or for example, models that involve large extra dimensions. And in all of these models, you have one thing in common, namely that neutrinos are getting one mass contribution from the Higgs condensate here at a very high energy scale. And therefore, these models have to explain why the small neutrino masses are suppressed with respect to the scale of the Higgs condensate. And this is, for example, done in the seesaw mechanism by having a very heavy right-handed Majorana neutrino mass, which is then suppressing the observed neutrino masses with respect to the Higgs condensate. Or if you look at large extra dimensions, this suppression is achieved by having a small overlap of the wave functions of the left-handed neutrino living in the 3+1 dimensional brane and the right-handed neutrino living in the higher dimensional bulk. So we're trying something very different. We don't go to high energies and we don't add any new particles to the standard model. We simply take the standard model as it is and we couple it to gravity, which can be done if we look at quantum gravity as a low energy effective field theory. So it's simply a minimal coupling to the gravitational sector. And what we saw is that gravity contains an inherent source of chiral symmetry breaking and therefore of mass generation. And this is precisely the case in the presence of a gravitational theta term. And this is what I will talk about today. So the summary is that in the presence of such a term, we showed that this generates a fermionic condensate, in particular in the neutrino sector, and this gives rise to small masses. And all of this happens at a new energy scale inherent to these gravitational effects. And this energy scale turns out to be numerically coincident with the scale of dark energy. So this is a brief summary of my talk today. Let me now go into the details. So we have this fundamental question of where the masses are coming from, and we're calling QCD for help, which means that we are first looking at some analogous effects taking place in QCD. And I would like to give you a summary of these QCD phenomena, which are very well known, just to give you an intuition for the main arguments behind our model on the neutrino side. So in QCD, we know that we have a theta term, which looks like this. So I omitted some numerical constants here in the front. And then you have a theta parameter, which is an angular parameter, could take any value between 0 and 2 pi. G is the gluon field strength, and G tilde is the Hodge dual of the gluon field strength, which is simply the epsilon tensor times the gluon field strength. So in the beginning, people thought that this term is irrelevant because it's a total derivative. So people thought you could just integrate over the 4 space-time dimensions to get your action, and then this term would simply disappear. So it's just a mathematical artifact and it's unphysical. However, it was shown later by Toft, Witten, and Veneziano that there are actually non-perturbative effects which make this term physical, and physical means that it should be physically observable, so this theta parameter should have physically observable consequences. So let me now remind you of what these non-perturbative effects are actually doing in QCD. So one particular consequence can be seen in the symmetry breaking sector of the quarks. So if we look at the lightest three quarks, the up, down, and strange quark, they are very light, so we can approximately treat them as massless. And then we have a fermion flavor symmetry, U3 vector times U3 axial, which is spontaneously broken to U3 vector. And this gives rise to 1 + 8 pseudo-Goldstone bosons, which are the mesons of QCD. So we have this eta prime meson and the 8 companions. And historically, it was a huge puzzle why this eta prime meson was much heavier than its 8 companions. And the resolution was precisely in these non-perturbative effects. And it was shown in particular that this eta prime meson, which is emerging from spontaneously breaking this U1 symmetry, which is a subsymmetry of this U3A, this symmetry is anomalous, which means that if we look at the divergence of the current corresponding to this U1 symmetry, then this is non-zero. So first of all, we have the mass contribution from the 3 quarks, because this is just an approximate symmetry, which is broken by the masses of the up, down, and strange quark. So this is that second term, which also gives a mass contribution to the pions, kaons, and eta meson. But on top, we have this very large mass contribution from GG tilde. So precisely from these non-perturbative effects, which also give rise to the theta term in QCD. So the last aspect of QCD that I want to mention is that the strength of these non-perturbative effects are measured by a quantity called the topological vacuum susceptibility. And it looks like this. So we have this correlator GG tilde in the limit of vanishing momentum. And in pure QCD, we know this is non-zero. And if we now couple the gluons to the quarks, it was shown in the 80s that there's an intrinsic relation between the susceptibility and spontaneous symmetry breaking in the quark sector, which is giving rise to a quark condensate. And I will talk more about this relation when I come to the neutrino side in the following. Not only QCD, but also gravity contains a theta term. This is something a bit less well known as in the QCD case. The theta term structurally looks very similar, so you also have some numerical constants that are emitted. You have a theta parameter, theta g. R is the Riemann tensor, and R tilde is the Hodge dual, so just the epsilon tensor times the Riemann tensor. So now there's one crucial difference between this gravity and QCD case, and the difference is that in gravity, it's not fully known whether this term is physical or not. And the reason is that just as in QCD, this term is a total derivative, so it might be that we can simply omit it from the Lagrangian. However, also in gravity, we have a lot of non-perturbative effects like gravitational instantons, wormholes, micro black holes, which could in principle contribute to this term. In particular, because we know we also in gravity have our degenerate vacuum structure and we have transitions between those. So it's very likely that the theta term in gravity exists, but in the end, this will depend on your full UV completion of quantum gravity and the formalism that you choose. So we don't want to enter this debate whether the term is actually physical or just a mathematical artifact. We simply take the physicality of this term as a starting assumption, and then we examine the effect this has on the standard model. And then if we observe these effects, potentially, if we can check on which energy scales these effects could take place, we can actually have an experimental insight on the nature of this term if we can see these predictions. So this is the idea, that we take it as a starting assumption and see if we can actually see these effects. It was shown already a couple of years ago by Dvali, Jakiv P, Folkerts, and Funcke that in the presence of the gravitational theta term, we have a lot of similarities between the topological sectors of gravity and QCD. So first of all, in both cases, we have anomalies such as this axial U1 anomaly. And on top of that, the topological structures are very similar, and we get a massive pseudoscalar degree of freedom in both cases. And in the QCD case, it's this eta prime. And in the gravitational case, I will show you in the following what will happen. So let's look at gravity coupled to neutrino species. And we look at neutrinos only at the moment because we treat them analogously as the lightest quarks of the standard model, because the neutrinos are the lightest fermions in the standard model. So if we have 3 neutrino species, we also have a fermion flavor symmetry in the neutrino sector, and this symmetry is exact if the masses are vanishing. However, we know that this subsymmetry of the U3 axial sector, which is precisely this U1 axial symmetry, this symmetry is anomalous in the sense that the divergence here of the corresponding current in the neutrino sector is non-zero. And this was shown already in the 70s, and this is widely used, for example, for early universe gravitational leptogenesis models. And it simply means that we have a divergence very similar to the QCD case, where we get a contribution from the neutrino masses if they were non-zero, and an additional contribution from this R tilde term, which also appears in the gravitational theta term. So now what we showed in our paper around 4 years ago is that also in the gravitational side, we can relate the topological susceptibility with the generation of a condensate. So if the theta term is physical, this is equivalent to having a non-zero topological susceptibility in the limit of vanishing momentum. So this is similar to QCD. And just as in QCD, we were able to show that this is generating a condensate. And the way how we can show this is by writing this R tilde term as the exterior derivative of a field. And we can treat this three-form field as a gauge field, write down the low energy effective field theory for this field, and then see how it couples to the neutrino sector. So this is very analogous to the QCD case. And I have to mention one aspect here, that the symmetry breaking and the condensation here can be rigorously proven only for this U1 sector, because we're using this anomaly equation to describe the coupling of these topological effects to the neutrino sector. And this is very similar to QCD. So in QCD, we can also establish this relation that I showed earlier between the susceptibility and the condensation only for the U1 sector. So the same is given here. And in QCD, what we usually do is to learn about the full symmetry breaking pattern. We have to go to experiments and see what the observations are telling us. And this is exactly the same here. So we can prove the condensation for one of the neutrinos, which means one of the neutrinos at least has to condense and get a mass through this effect. But for all the other neutrinos, what we have to do is to go to observations and see what kind of symmetry breaking patterns could we get. So the first thing we see when we look at the observations is that we have non-zero neutrino masses, and these are hierarchical. So if we now want to generate neutrino masses through this effect, then we have to break the flavor symmetry in the neutrino sector much further than in the QCD case. Because in QCD, this mass contribution through the condensation is equal for the 3 flavors. So we have an equal contribution to the up, down, and strange quark mass from the quark condensate. And in our case, we want to have hierarchical masses, so different masses for the 3 neutrino species. And this means we have to break the symmetry down to U1 cubed. And this means that we're getting more Goldstone bosons in this case. So from this U1 sector, we get a meson, like a neutrino meson, called eta nu. This is this massive pseudoscalar degree of freedom. And on top of that, we get 14 massless bosons, which are arising from breaking the rest of the symmetry. So let me give you an overview of the condensation part of the model. And on the next slide, I will talk about the mass generation part. So as I mentioned on the previous slide, we will have these non-perturbative effects. They're either semi-classical or fully quantum, and they're giving rise to a physical theta term in pure gravity, which is analogous to saying this topological vacuum susceptibility in the gravitational sector is non-vanishing in the limit of zero momentum. So this is the starting assumption that we make. And the first thing we observe is that this inherently introduces a new energy scale into the system. And this is the scale which is setting the strength of this correlator, of these non-perturbative effects. So in QCD, this would be the QCD scale. On the gravitational side, this is, first of all, a free parameter, because we're not making a specific assumption about the origin of this term and of the susceptibility. So we're taking it as a free parameter and constrain it with phenomenological requirements. And this is what we will see later in the talk, that phenomenologically, there's only a very small window where these effects are still allowed to take place. And this window is in between the milli-electron volt and electron volt energy scale. So from a theoretical side, the only input assumption that we have here is that the scales should be very strongly suppressed with respect to the Planck scale, because non-perturbative effects are always either exponentially or power law suppressed with respect to the cutoff scale. So this is the pure gravity side. Now if we couple gravities to neutrinos minimally, we see that this is inducing Flavor symmetry breaking in the neutrino sector, and we were able to prove this by using this gravitational anomaly equation, which I showed on the previous slide. And as I mentioned, this gives rise to a condensation of neutrinos, and this is happening below this new energy scale lambda g. And this gives rise to this massive eta nu boson and 14 additional massless goldstones. And the reason why these 14 additional goldstones are massless is that the neutrinos, they don't have a mass to begin with. So we assume that they're massless in the standard model. And this means that this is different from the QCD case, where the quarks are already getting a hard mass from the Higgs condensate. So now let me come to the mass generation aspect. So the same coupling which is giving rise to the condensate is also giving rise to the mass generation. So we get effective small neutrino masses through the coupling to the condensate. And this is very similar to QCD. So in QCD, we have a 't Hooft vortex, where we have the up quark here, the down quark here, the strange quark here. In the neutrino sector, it's very similar. So we have the 3 different neutrino flavors here, and this diagram is then contributing to the electron neutrino mass. Here we have the non-perturbative effects, which are giving rise to the susceptibility, and these crosses here are denoting the condensates in the neutrino sector. So this means that we're not making any additional assumption when we say that the neutrinos are getting a mass through the condensate. This is something which is very well known in QCD. So now you might ask the question, how can we get hierarchical neutrino masses if gravity is coupling equally to all the fermions? And the answer to this question is that it's a spontaneous symmetry breaking effect. So gravity is equally coupling to all the fermions, but if you write down the most generic effective potential of all the neutrino bilinears entering in this, for the order parameters, the flavor invariance in the neutrino sector entering this potential, you see that if you already include up to quartic order invariance, you see that you can have a very rich variety of symmetry breaking patterns. So this means you can get hierarchical masses, you can get equal masses, you can just get a mass for one of the neutrinos, or for all of them. So we can't make a prediction precisely for how the mass structure should look like, but we can allow for this hierarchy. And in particular, because this gravitational origin of the mass is fundamentally different from the mass generation of the other fermions in the standard model, we would expect that we get a large mixing in the neutrino sector compared to the quark sector. And this is something that we actually observe in nature. So the last aspect I would like to mention on the theoretical side is that the mechanism works for both Dirac and Majorana masses. So far, I focused on the Dirac case. This is why I wrote a neutrino and an antineutrino here, and also in the previous slides, because then it's a bit more intuitive to compare to the quark sector. So there we have then a U3 cross U3 symmetry. But if we only look at left-handed neutrinos as we have them in the standard model, then of course the symmetry would be reduced. We would have only one U3 symmetry to start with. But also in this case, the entire computation would go through. So we would have a condensation in the Majorana neutrino channel, and this would give rise to Majorana masses. And this would be the most minimal part, the most minimal realization of the model, because then we don't need to add any new particles to the standard model, because we just have the left-handed neutrinos and we don't even need to add the right-handed ones. So this is the summary of the theoretical part. Let me now come to the constraints on the symmetry breaking scale, because this is the most important part where we need to understand on which energy scale these effects can take place. So in principle, we have three different energy scales. First of all, we have the scale of the neutrino condensate. Then we have the scale of the chiral symmetry breaking. And we have the temperature in the universe where this phase transition is happening of the condensation. In principle, all these three different scales are different, but for simplicity, we can assume them to be equal to see what different constraints we have on those, but keep in mind that parametrically they're different, so these constraints will be slightly modified. Now we have several upper bounds, and in particular, from the standard model itself. So now what's becoming relevant is that gravity is not only coupling to neutrinos, but also to the other fermions of the standard model. So in principle, also the electron, the quarks, and so on and so forth, will get a contribution to a condensation and to their masses. However, this is very strongly constrained from standard model precision measurements. For example, if we had this condensation mechanism at the Planck scale, and a mass contribution to the fermions at the Planck scale, this would be observationally ruled out. Similarly, if we had a quark condensate at the QCD scale, this would contribute to the masses of the W and Z bosons, which is also ruled out. For the electrons, we would get an additional interaction in the electronic sector. This is also ruled out, and this is pushing the constraints on this energy scale to below electron volt. So for all energy scales above, these effects can't exist. From cosmology, we have even more precise constraints. And the constraint here is that the scale has to be smaller than 0.3 electron volt, because this is the temperature of the universe when photon decoupling happened. So the formation of the CMB. And we know that in the neutrino sector, in the early universe, we have to have neutrino free streaming, so no interactions in the neutrino sector. Very strongly suppressed interactions would be allowed. But in our case, because we have a phase transition in the neutrino sector, and this is yielding to neutrino self-interactions, this can only happen after photon decoupling in the very late universe at temperatures below 0.3 electron volts. And I will talk more about this phase transition on the next slide. Now there's also a lower bound. So there's one model-specific one. If we look at the mass splitting of the neutrinos, which has been observed experimentally, we know that the heaviest neutrino at least has a mass of 50 millielectron volts. So with a maximal coupling of 4 pi to the condensate must be at least 4 millielectron volts. Then there's another bound coming from the gravitational sector, because we have measured gravitational interactions, so Newtonian law, for very large distance scales. So all the way down here, large distance scales corresponding to low energy scales, and up to the energy scale of millielectron volt, which is corresponding inversely to distance scales of around millimeters, micrometers. So all these effects that we're discussing are ruled out at low energy scales and at very high energy scales, completely model independently. So there are these model dependent constraints from cosmology and the mass splittings, but they're also model independent ones from the standard model and gravity. And now we see there's only this small window left open, and we observe that we get a neutrino vacuum condensate, nu bar nu, in this regime. And we see that it's numerically coincident with the scale of dark energy. So dark energy has an energy density in the universe of around millielectron volt to the power of 4. So this is precisely here the energy scale that we are looking at. And we can't really solve the cosmological constant problem, because we can't explain why the quark condensate, for example, should not contribute to dark energy, or the Higgs condensate should not contribute. So the only thing we can say here is that we have a condensate which is numerically coincident with what we observe. And this is the only condensate which is inherently connected to the gravitational topological sector and the vacuum structure in gravity. So there might be a connection. So let me now come to the predictions on the cosmological side. And I think the most interesting prediction is that the neutrino mass bounds that we usually infer from cosmology, they're substantially weakened. And the reason is that the relic cosmic neutrinos from the Big Bang in the universe, they're massless through almost the entire universe until this very late phase transition at temperatures smaller or equal to this symmetry breaking scale under G. Then in this phase transition, the neutrinos are getting the masses. However, directly afterwards, the neutrinos are decaying into the lightest eigenstate. So you have your heaviest neutrino decaying in the second heaviest, decaying into the lightest one. So you're only having neutrinos left over in the lightest mass eigenstate. And I will talk more about the decays on the next page, how they exactly take place. And after this decay, the neutrinos are annihilating. So a neutrino and an antineutrino could annihilate into these bosons that I talked about previously. So we have these additional 14 massless Goldstone bosons, and the neutrinos and antineutrinos can annihilate into those. So if we have an equal number of neutrinos and antineutrinos in the universe, then neutrinos would completely disappear in the late universe. And this would mean that we have a neutrino-less universe, which would be interesting observationally, because as far as I know, all other kind of models that are predicting neutrino-less universes, they're usually modifying early time cosmology that strongly that they're already ruled out by precision measurements of the CMB. But in our case, the phase transition is happening after CMB formation. So in our case, you can't actually see in the CMB that the neutrinos are disappearing afterwards. So this disappearance of the neutrinos, this annihilation into the massless Goldstones, this is eliminating the standard bounds that we have in cosmology for the sum of the neutrino masses. Usually this is around 0.12 electron volt. These are the latest Planck results. And in our case, we could have much larger masses, because in our case, the only constraints on the masses that we can trust are the ones from terrestrial experiments like the Katrin experiment, which is a beta decay experiment. So the latest results from Katrin imply that the mass of the electron neutrino has to be smaller than 1.1 electron volt, which means the sum could be around 3 electron volt, which is more than an order of magnitude larger than would be allowed by standard cosmology. So the Katrin experiment can probe the neutrino masses down to 0.2 electron volt for this electron neutrino. So it would be very exciting if Katrin could actually measure these masses, because this would be in conflict with the standard bounds, and it would be okay in our case because we have evaded those very strong bounds from cosmology. On the other hand, cosmological surveys are hoping to detect the neutrino masses within the next 5 to 10 years. And one prediction of our model is that these surveys won't see the masses. So if these surveys are actually detecting non-zero neutrino masses cosmologically, then I would say the model is ruled out. Of course, you can always add more stuff. So you could assume you have more neutrinos than antineutrinos in the universe, and then this annihilation won't go through completely, so you would still have some neutrinos left and you could see the masses, but this is an extra ingredient that you have to add. So if you look at the minimal version of the model, cosmologically you should not see any neutrino masses in the next 5 to 10 years. And another aspect which is cosmologically relevant, if you add additional sterile neutrinos, you would get inherently masses that are small, so you would have light sterile neutrinos, and they would be cosmologically allowed, because usually you get into these conflicts that you get a contribution to the sum of the masses, and this is very strongly constrained, which isn't the case in our model. And on top of that, you have a contribution to the number of effective degrees of freedom in the early universe, which is also not the case in our model, because the neutrino masses and therefore the interaction between the sterile and the active neutrino species are zero in the early universe. So they're completely decoupled, these sectors. So this is cosmologically the most precise prediction of the model that can be tested in the next 5 to 10 years. One other thing we looked at is the impact on other cosmological parameters. In particular, we looked at sigma 8 versus omega m, because back when in 2018, when we wrote this paper, there were cosmological tensions between the Kids Week lensing data set and the Planck data set precisely for these parameters. So you see this small tension here, it's quite small. It was just around 2 to 3 sigma. And we were checking if our model could actually change this prediction, but we saw that it's just broadening up the parameter space and not really bringing these two a little bit discrepant data sets more into agreement. And the same is true for the Hubble tension, which is the most famous cosmological tension. The model is not really alleviating the tension, so this is something we checked. Another thing we checked is what kind of impact this has on the dark energy parameter, and here we see an interesting effect. Because usually if we look at lambda CDM plus neutrino masses, we see that omega lambda is around 0.7. So we have around 70% of dark energy in our universe. But now in our case, this could be substantially reduced. And the reason is that we have this phase transition in the very late universe, and we could have either a second order or a first order phase transition. And if it's a first order phase transition, we get trapped in the false vacuum for a long time before we can tunnel to the true vacuum. So we have a substantial amount of false vacuum energy, which is just the difference in vacuum energy between the wrong and the true vacuum. And this is contributing to dark energy. So you have a superposition of this effect and the standard omega lambda, and this is possible to reduce the omega lambda that you have besides the neutrino sector. And the larger the neutrino masses, the stronger the suppression could be. On the other hand, it would of course be interesting if we had the complete dark energy in form of this false vacuum energy. And this would mean that in the very late universe, this dark energy component decayed away, and we're actually living in a local bubble without having any dark energy, which is then expanding into the universe. But of course, this would imply that we had a very, very recent phase transition. So we would need to have some coincidence that the neutrino masses would be generated very recently in this phase transition. So it could also be that it happened much earlier, then there wouldn't be any tuning of the time of the transition, but then the impact on the dark energy sector would not be that dramatic, as I showed here. So now let me come to the astrophysical sector. And here the most interesting aspect is that neutrinos are decaying. So this is something I already mentioned on the previous slide. So we have a decay of a neutrino into another neutrino and one of these Goldstone bosons. And this means that if the neutrinos are traveling from far away to Earth, they would all decay into the lightest eigenstate. And if we have, for example, a normal mass hierarchy, the lightest eigenstate is predominantly consisting of the electron neutrino. This means that we have a distinct flavor pattern of neutrinos at Earth if the neutrinos are traveling a long enough distance to Earth. And this is, for example, the case for ice cube neutrinos or supernova neutrinos. According to our model, all of these neutrinos should be in the lowest eigenstate when they arrive here at Earth. And this is something that IceCube is currently probing already, but we don't have enough data yet. But this will be probed in the upcoming years with more statistics. So one additional contribution where, so an additional contribution to getting insights from these decays is that Majorana and Dirac neutrinos are decaying differently. So this is something we just observed like 3 years after we wrote the original paper, is that we have different decay channels. So if we have a Dirac neutrino, then a neutrino can decay into a neutrino plus one of these bosons. But it's not allowed that a neutrino decays into an antineutrino because this would violate lepton number. In the Majorana case, this is of course allowed because lepton number is broken anyway. So we have different decay channels, and in principle, we can observe this in data. For example, if we look at the energy distribution of the daughter neutrino. So this is the distribution of the J neutrino here in this decay as a function of the relative neutrino energy, then you see that the Dirac and Majorana cases are giving different energy distributions. So the Dirac case is this orange triangle here, and the Majorana case also allows for this blue triangle. So in total, for the Majorana case, we have this box, while for the Dirac case, we just have this triangle. And this is for a very large mass hierarchy. Here we have almost degenerate neutrino masses, which are also still allowed in our model. So here the energy distribution looks a little bit different. So now the question is, can we observe this in data? And in principle, the answer is yes, but of course we need to understand the energy distribution of the neutrinos at the source before the decay very precisely in order to distinguish these two different scenarios. And with our current knowledge of the astrophysical origin of neutrinos, it's not yet possible to measure these different energy distributions, but it should become possible if we have a better understanding of the creation mechanism of the neutrinos that we're, for example, measuring at IceCube. But one aspect which should be observable is that we have antineutrino appearance, for example, for solar neutrinos. So we know that the sun is emitting predominantly electron neutrinos. We haven't, sorry, neutrinos and not antineutrinos. So we haven't observed any antineutrinos from the sun yet. But if neutrinos are Majorana particles, these neutrinos that are produced in the sun, they could convert into antineutrinos while they're traveling to Earth. And this decay time of the neutrinos is exactly at the threshold of the neutrinos traveling from the Earth, from the sun to the Earth. So this is precisely the distance at which these neutrino decays become relevant. So it would be very exciting if we could actually detect antineutrinos from the sun, particularly in the very low energy regime where we haven't detected a lot of solar neutrinos yet. And this would be a hint that we actually have Majorana neutrinos, which are experiencing a strong decay and transition from neutrinos to antineutrinos. So the last aspect of the phenomenological consequences are concerning gravity and new particle detection. So on the gravitational side, one thing I find interesting is that we have in principle different polarization intensities of gravitational waves. So this was something first observed in the context of Chern-Simons modified general relativity by Jacques and P in 2003. And in the beginning, we were very excited when we realized this, because we published our paper in the year when we had the first gravitational wave detection. So we hoped we could actually see this in the experiments. But when we worked out how large these effects actually are, we realized that it's quite far away from the sensitivity of current gravitational wave detectors. So this is more interesting on an academic level, but not for experimental observations at the moment. So one aspect that is actually relevant for current experiments or the next generation of experiments is the fact that these Goldstone bosons, these phi bosons, they can couple through photons via an intermediate electron loop. So you have these phi bosons, they are connected to electrons through this non-perturbative gravitational vertex, which is very strongly suppressed. But if you look at the entire transition amplitude from the phi bosons to the photons, you can actually see that the decay constant of these axion-like phi particles is very similar to axion-like bosons, which are currently searched for in axion search experiments. And one experiment which will become relevant in the near future are these shining light through walls experiments. So in these experiments, you have a laser, so you have photons coming in, converting into axion-like particles in an external magnetic field. Then they are passing through a wall and then get back converted into photons and can get detected. So in our case, it would be the phi particles that could pass through the wall in those experiments. And the interesting aspect to see here is that if we look at the decay constant, this is actually in the reach of the next generation of these experiments, but it would be already ruled out by astrophysical constraints if these constraints were applied to the phi bosons. And now the interesting aspect here is that these phi bosons are composite particles formed at very low energy scales with a very low binding energy. So they're actually dissolving in astrophysical, very high energy, very high temperature environments. So this means that the astrophysical constraints on these bosons are not actually applicable, but for axion through walls experiments, shining light through walls experiments, the constraints are actually important. So if these experiments see something, but astrophysical constraints don't, then this would hint towards some kind of mechanism of having composite axion-like particles, like in our case. So this is a way of of having new physics at low energy scales hidden due to the compositeness of these particles instead of having it at high energy scales, and it's hidden because of the high energy scale and the suppression of new physics due to the high energy scale. And this is something we discussed in another paper called the domestic axion paper, where we saw that the same effects that could give rise to neutrino masses could also explain the strong CP problem. And I see there's something in the chat. Okay, maybe I will just briefly finish the talk and then answer this question, because it's just 2 more points. So then I will come to the summary, and so maybe it's it will be better to just have all the questions at once. Okay, so I just wanted to mention as the last part of the phenomenological section that there's some ongoing projects. So one aspect is that we are looking at the topological defects that form in this phase transition in the late universe. So we will get strings, domain walls, monopoles, and neutrino fermions, and all these defects, they are dependent, of course, on the Dirac or Majorana nature of the neutrinos, and we have examined the formation mechanism and the evolution, and that's something we hope to put on the archive soon. And another aspect is that we are reconstructing the mass of the neutrinos as a function of cosmological redshift. So we have different data sets at different cosmological redshifts, and are currently looking at the mass constraints from those, because we saw in our previous investigation that cosmological data is preferring larger masses in the late universe compared to the early universe, and the onset is precisely at the onset of dark energy. So this was something we found very interesting, and that's the reason why we now model independently, reconstruct the neutrino mass as a function of time. And this is very similar to like reconstructions of the dark energy parameter or the Hubble constant as a function of cosmological time. So this brings me to my conclusion. To sum up, we started with this one assumption that we have this theta term in the pure gravitational sector. And I mentioned it's still an open question whether the term is a mathematical artifact or really physical, but there are a lot of non-perturbative effects that can very likely make this term physical. So we examined on which energy scales these effects could take place, and we saw it has to be below the electron volt and above the milli-electron volt scale. So we saw that at this scale, this gives rise to condensation, and the neutrinos would be the main particles affected by this. This gives rise to small effective neutrino masses and is independent of any Higgs or seesaw mechanisms. So there are more details on archive, in particular these 2 papers. The first one concerns the neutrino mass mechanism. The second one is the one I mentioned on the previous slide about the strong CP problem and how we can solve it. Then on the phenomenological side, we saw that we can still have very large neutrino masses in cosmology, which otherwise would be ruled out. And we have the possibility of having an additional contribution to dark energy, or even the full contribution, and have the possibility that it decays away in the late universe. Then we saw that we have enhanced neutrino decays, which are different for Majorana and Dirac neutrinos, and which can be measured for example, at IceCube or solar neutrino experiments, and in particular, the mass signatures can be observed at the Katrin experiment and in the next generation of cosmological surveys, like Euclid, for example. And these phenomenological aspects are written down in these 2 papers, and I hope there will be 2 more coming up soon. So stay tuned. And thank you very much for listening. And if you have any questions, feel free to ask them now.
Thanks, Lena, for a really nice talk. That was quite nice. So we have time for plenty of questions. I saw Emmett already put one in the chat, if you want to have a look at that.
Yeah.
And then anyone else, feel free to raise your hand.
Okay, so Amit was asking the question why there's a reason why we considered a gravitational theta term to generate the condensate. Naively, one would expect that since the theta term arises in QCD, Sorry, the question was intended for after the talk. Yeah, no worries. No, I mean so we have two different theta terms. We have one in QCD, one in gravity. The QCD one is only affecting the quarks because QCD, like the gluons, are only coupled to quarks and not to neutrinos. So we can't generate a neutrino condensate from the theta term in QCD, but we could only generate it through a theta term of some gauge sector which is coupling to neutrinos. And one of these sectors is gravity. So that's the reason why we looked at this one. So we have condensate contributions from this theta term for all the fermions, but for the ones with a large mass, these are very strongly suppressed. So only the neutrino will be the one that's feeling these effects. And yeah, on the other hand, for QCD, we also have lepton condensates connected to the theta term. So was this answering your question? Or?
I mean, I guess it's a little, it doesn't have, maybe it's a little bit beyond what you've done, but like, I was just wondering, like, wouldn't you expect the theta term also for SU2L and therefore a lepton condensate? Like, would this work? Yeah.
Sorry, yeah. So you mean SU2L, you mean the weak sector?
Yeah, yeah, sorry, yeah. Would you have an anomaly in the weak sector and then...
That's a very good question. So, yeah. So in the SU2 sector, in principle, we should have a theta term as well. You have the same non-perturbative effects. You have this theta vacuum there as well.
Yeah, yeah.
But the weak sector is special because it's only coupling to left-handed particles.
Yeah,
so what you can do is you can always rotate the theta term away.
Yeah, you have chiarosymmetry.
Yeah. So in that sense, the theta term is unphysical. So this is why I in the beginning was putting such a focus on whether something is physical or just a mathematical artifact.
Yeah.
So in SU2L, it's a mathematical artifact because we can simply get rid of it. But if we had some B minus L violation in the standard model, if we added, then we could actually make this term physical as well. And this is something that has been discussed by people looking at grand unified theories, for example.
Okay.
Yeah.
So, wait, does it not work only because the neutrinos are massless? Because the neutrinos are left-handed, or like? Oh, sorry, no. SU2 only couples to left-handed. Sorry, my bad. Yeah, I get it.
Mm-hmm. Yeah. So for SU2L, you don't have there.
Yeah.
Not from the crowd. Mm-hmm. Okay. So.
Thanks. Oh, thank you. Yeah.
I hope this answered your question. So there's another question I see in the chat. Whether
I think there were some raised hands before, so I think Ning Chang got in there first.
Okay.
Thank you, Lena, for the very nice talk. So I have 2.5 questions. The time is allowed. So my first question is that I can imagine that if you have stereo neutrinos, it could also form some kind of condensate and couple to the Ricci scalar. In that sense, that means the stereo neutrino can still talk to the active neutrinos in the early universe.
So the stereo neutrinos and the active ones, they would both get a condensate in this case, and both get a mass, and they would be of similar orders. So you could have like unvolved stereo neutrinos, for example. So you could have in principle these mass splittings that they observe with these anomalies, but I mean these anomalies are including each other somehow with appearance and disappearance. So I'm not really trusting them to be some signature of light from neutrinos. But if you want to have that neutrinos in the universe, yeah, you would have this mass splitting and the suppression, the coupling between the sterile and the active one would be extremely strongly suppressed in the universe. So even before the condensation and the mass generation, you have a small coupling, but it's exponentially suppressed. So it's similar to the axion mass generation. If you look at axion models, the mass axion is exponentially turning on as a function of temperature. So it's like 0 in the early universe, and then it's very rapidly turning on at the transition. And here it's very similar. So these effects will turn on so extremely rapidly that before photon decoupling, you won't be able to see them. And this is where the constraints on the number of degrees of freedom in the early universe is coming from. So you won't have a contribution there.
Okay, thanks. I think I understand. Another question is that what is actually the neutrino lifetime you would predict? Because I got the impression that like in later universe, or even if we consider high-energy neutrinos that we can observe at the ice cube, then all these high-energy neutrinos would decay to the latest state, like the new ones. And there we will see like mostly electron neutrinos at ice cube. And Aaron can correct me if I'm wrong, but it seems that the flavor contour that we expect very recently from ice cube results would be centered somewhere near the 1:1 equal flavor ratio and far away from the pure electron neutrino case. If we include the through-going muons and all these information at ice cube.
So it wouldn't be purely electron. I think it's around 50% electron neutrino contribution. So it's definitely dominant. So it shouldn't be 1:1 in the triangle. So yeah, as far as I know, it's true. Currently with ice cube, we have the 1:1 is favored compared to the complete decay scenario. But as far as I know, it's around the like 2 sigma level, and we are not really having enough data to actually decaying or not. Maybe Aaron knows more about the latest.
Yeah, actually, I think the three of us should have a chat later on about this. I think the answer is that there is enough data, but Ice Cube has not done the analysis.
Ah, okay.
So the last combined analysis was only using 2 years of data.
Yeah. I think this was the one that we cited in our. It was around.
Yeah. So the projections for that exist, like what it should be now, but that analysis hasn't actually been done.
Ah, that's interesting. So when does it come up? We're only constraining the model. It's really in the center.
Yeah, so if we look at the ice cube 80-year data, and if we compare with the new one only analysis, that the complete decay case is almost ruled out. Well, but anyway, that is just a projection. It's not real results.
Yeah, so it could be completely detected.
Yeah, so that's cool. Okay, I didn't know that it would be that quick. I thought I would need to wait much longer. I mean, in principle, you could also have an inverted hierarchy, but I mean, we know that currently favored to a normal one, so we should look at both options.
So
that could the inverted one also be ruled out too with this projective?
I don't think so. I think it's
well, the inverted one is also a little bit far away from that ice cube 80-year contour. If you look at our figure 3 in the draft, but anyway, that is just that is not.
Yeah, no, I think we should have a chat about this. I do want to get to Art. So Art, you had your hand raised.
Yeah, I'm wondering about the effects of your model in neutrinoless double beta decay, both in terms of overall detectability, but also in things like if you do detect it, then would the correlation in the electrons emitted be a way of distinguishing your model from Seesaw or something else? Have you looked at that at all?
So we looked at it, and we haven't actually found an agreeing conclusion if we compare all the different views on it. So in the beginning, we thought that because it's a high temperature effect, the masses should dissolve at this vertex in neutrinoless double beta decay because you have a large momentum transfer there in the sector. But when we actually made the computation, one has to insert the vertex at it's an on-shell p squared equal m squared situation where there doesn't seem to be a large momentum flow through the vertex itself. So we haven't found a concise conclusion about that yet. So we were intuitively expecting that it's vanishing, the neutrinoless double beta decay rate, but when we made the computation, it seemed that it's just not distinguishable from the Seesaw case because the condensate is not actually dissolving in this in the decay computation.
So the sort of predictions that are made based on Seesaw for a given set of masses as observed today are still relevant for that for that process. Thank you.
So it goes against the original intuition that we had, but we made the computations, and it's still similar to like exactly the same as the Seesaw case. Yeah. So the mass are just not dissolving. Yeah. And then
nice
of course.
Thanks a lot.
Yeah.
Very nice. Thank you.
Thanks.
There's a chat in the question, a question in the chat from Jean-Francois, who says, does your model need the neutrinos to not get a mass from the Higgs mechanism? Or is it just that that would be small compared to the condensate contribution?
Yeah, that's a good question. So in principle, we just saw there is a mass contribution that could be there on top of any other mass contribution. We could have a seesaw mechanism, Higgs mechanism contribution, and then the gravitational contribution on top of that. If we had only the left-handed Majorana neutrinos, there would not be any mass from the Higgs mechanism. So then this could be naturally just the only contribution coming from the gravitational sector. If we have a right-handed neutrino, then of course there's the question, if we have a left and a right-handed one, why shouldn't we get a contribution from the Higgs mechanism, which is of order of the Higgs condensate? And that's the question I can't answer. So you either have to impose some additional symmetry that's preventing this specific coupling, because intuitively the gravitational contribution would be much smaller than the ones from the Higgs condensate. So in that sense, from a theoretical side, in the model, the Dirac case is not that nice, because you need some additional mechanism to explain why there's not a mass coming from the Higgs mechanism. And that's the reason why I would theoretically favor the Majorana case, because in that case, the contribution from the Higgs mechanism would be completely absent. Does this answer your question? Yes, okay.
Maybe very quickly, since I don't see any other hands raised, does the model say anything about hierarchy? About the neutrino mass hierarchy? Whether
it's normal or inverted?
Yeah.
Yeah, it doesn't.
Or you can either one.
You
works.
can have any kind of symmetry breaking pattern, yeah. So the only thing we see is that we would expect to have a large mixing in the neutrino sector, because that's because of the mismatch between the two mass pieces. So that would be large, but apart from that, for the structure of the neutrino masses, there's no prediction. Yeah.
Okay. I don't see any more raised hands unless your hand is still raised. I'm assuming that's from before. So let's thank Lena again for a really nice talk. We'll clap for everyone. And that concludes our seminar series for the fall. So everyone have a safe and enjoyable holiday season. And I'll see you all at some point in January, I guess.
Thanks.